Chapter 12. The first section in Chapter 12 is tangent lines. So we're going to be talking about circles and lines that are tangent to the circle. So a tangent, this will always be a line, it intersects the circle at exactly one point. That point there is the point of tangency. So point Q in this case is where the circle and the line intersect, so it's the point of tangency. There are a few theorems that go along with tangent lines. So, the first one here is Theorem 12.1. If a line is tangent to the circle, so if we're told that this line is tangent to the circle, then we know that the line is perpendicular to the radius. So, this is the center of the circle, and then here's the radius, and it's drawn to the point of tangency. So we know that these two lines, the radius and then the tangent line, are perpendicular. So if the line is tangent, then these lines are perpendicular. So the converse to that is that if we have a line that's perpendicular to a radius at its endpoint on the circle, so that's right here, then it's tangent. So if these two are perpendicular, then we know it's tangent to the circle. So those are converses of each other. We've seen those before in past chapters. So here's an example of how we might need to use this information to solve for missing links or just proving if this is actually a right triangle or not. So our question here is the line M, that's this line here, is it tangent to the circle O? So we would need to know that this is a right triangle. So because we would need a right angle here for these to be perpendicular. So if we know that the radius is 7, and then it told us that this length here is 24, and then it told us that this length is 18. So it's common here in this chapter that we need to know that from the center of a circle to the outside of the circle, that's the radius. We've known that for a long time. But here, we need to recognize that that's also a radius, because we need to know the length of this whole side, which is the hypotenuse for this right triangle. So we have 7 here. And so 7 plus 18 gives us the length of the whole hypotenuse, which is 24. So now you see over here, we're checking to make sure this is a right triangle here. So we have 7 squared plus 24 squared, because those are the two legs, and then equals 25 squared. We do the math and we find out that these are equal, which we learned back in a previous chapter that this means that this is a right triangle. That means this is a right angle, which means these two lines are perpendicular. If a line is perpendicular to a radius at its endpoint, then it is tangent to the circle. So yes, M is tangent to the circle. So we use this symbol, a circle with a dot, that's the center. We use that as the symbol for circle. If we do just a circle like this, we might think it's an O or a 0. So you have to put that point in there to say circle. So that's why we have this in quotes here. So that's that theorem. There's another theorem, Theorem 12.3. This is the two tangent theorem. So if we know that two segments are tangent to a circle and they're drawn from a common exterior point. So this point is called an exterior point because it's on the outside of the circle. And so if these lines are both drawn from the same point, then they are congruent, and if they're both tangent, they have to also be tangent. So we know this because if we draw in these radii, we know they are congruent, and then we know these are tangents because it told us this, so we know these are right angles. And then back in chapter 4, we learned that we can use the reflexive property to say that these two, since they share this side, that this is also congruent. So we can prove that these two triangles are congruent by hypotenuse leg. This is all back from chapter 4. And when we prove that those are congruent, then by corresponding parts of congruent triangles are congruent, that was CPCTC, we can say that NP and OP are congruent. So that proves this theorem here, that two segments tangent to a circle drawn from this common exterior point are congruent. So we've proven that this line NP and this line segment OP are congruent. And we can also show that the angles formed by the line from the center of the circle to the common point are also congruent. So these two. Because again, corresponding parts of congruent triangles are congruent. That was CPC-TC. So we might need to use that information that OP and NP are congruent, or that these two angles formed by this line made here are also congruent. So we have a few more vocabulary words that we might need to use because it might not give us a picture. We might have to draw a picture. So it might say that the circle is inscribed in the triangle. So this circle here is inscribed in the triangle. And the triangle is circumscribed about the circle. So we might see a problem where it says, draw a circle inscribed in a triangle. So you would draw a circle inscribed in the triangle similar to this. Or the triangle can be circumscribed about the circle. So this describes this same picture right here. So each side of the triangle is tangent to the circle, just by definition of these two words, inscribed and circumscribed. So this line is tangent here. So it intersects it in just one point. And if we drew in this radius here, they would be perpendicular. Let's look at some examples. So if we were needing to find the perimeter of a polygon, and it had a circle here inscribed in this triangle, this would be a common point out here that these two segments come from. So if we know this one's 4, then this one's going to be 4 as well, because of the two tangent theorem, which we just talked about. That was theorem 12.3. You can go back and look at it if you need to. So if this is 4, then this is 4. So it gives us also that this is 5, so this must also be 5. So the whole length of this side is going to be 9. And then again it says here this is 3, so then this must be 3. Again, this is all of these. We know that this is 3, and we know that this is 4, and we know that this is 5 because of the two tangent theorem. So now if we need to find the perimeter, there are a variety of ways you can do this. You can just add up each of the sides. Here we did that there's 2 times 5 because we have 2 5s here, 2 times 3, and then 2 times 4, and we get 24. You should get the same thing if you were to add up 8, 7, and 9. Okay, here we go. We're moving on to this one. We're also finding the perimeter in this case. So it's the same idea, it's just maybe a little bit harder to see here because there's a lot of writing on it. But if this is 5 here, that's from this tangent point to the exterior point here, then we know this part is 5. But it tells us that this entire thing is 12. So we need to know what we know about, we need to use what we know about segment addition to know that 12 minus 5 gives us 7. Because we need to know that information here. So because now if we know this is 7, that's from this line, if you can see it, to this line, then we also know that this part is 7, from here to here, which is why we wrote 7 here. Then if we know the whole thing is 11, then we get 4, which gives us this piece here, which is 4. So then we keep going around, and we get 6. And then we can know that this is 6 as well. If we subtract, we have to do 10 minus 6, we get this portion is 4. And then we get back here to 4 because of these two, again, from the two tangent theorem. So we again take the perimeter any way you would like to. In this case, we did 2 times 4, that's here, 2 times 5 here, 2 times 7 here, 2 times 4 again, and then 2 times 6. And that will give you the perimeter of 52 feet. So you need to use segment addition as well in a lot of these problems. So here, if we need to find the value of x in each of these diagrams, so we'll start out with this one. We know this is a how many sided figure? 1, 2, 3, 4. So using what we know about the sum of the degrees of a polygon, we can use n minus 2 times 180. So we get that the sum of all the angles of this quadrilateral will be 360 degrees. We already know that this is 130 degrees. And then these are tangent lines. So that means these are perpendicular. So we have two 90-degree angles. So we have x plus 90 plus 90 plus 30 equals 360. We solve for x and we get 50. So something that was written at the very top of the notes up here was that lines or segments that appear tangent are tangent. So we needed to remember that here. So it didn't need to tell us that because it told us up higher. We were able to assume that these were tangent. So now this one, we have this tangent line. We can assume again that they are tangent because it told us up above that they are. So we're going to start with this smaller radius. We're going to draw this as a parallelogram so that we can use that opposite sides are congruent. So if this whole segment is 3, and this is 2 because opposite sides of this parallelogram are going to be congruent because we drew this in that way, then this would be 7 and this would be 7, and we'd be left over with 1 over here. So using the Pythagorean theorem, we can solve for this because this is a right triangle, because this is a right angle formed by these perpendicular lines. So we have x squared plus 1 squared equals 7 squared. We get the square root of 48. Using what we know about simplifying radicals, we get 16 times 3 would be in here, and then we can do 4 square root 3. So that's our value of x using simplifying radicals. Our next example, we need to again solve for x. The length, so we have here again a tangent line and a radius, so these are perpendicular, forming a right angle, and then a right triangle here. We know that this side is 8, so we're good to go. And then we know that this side is x plus 2, so we can call the whole thing x plus 2 here. And then this is also x because this length here and this length are both radii. So we have x squared plus 8 squared equals x plus 2 squared. So up here I've done x plus 2 times x plus 2 because that's x plus 2 squared. We make sure to FOIL it out and we get x squared plus 4x plus 4. So we have x squared plus 64 equals x squared plus 4x plus 4. These x squareds are going to cancel out when we subtract x squared from both sides. And then we're going to subtract the 4 and bring it over here, so we get x is equal to 15. And it might ask you to plug it back in and actually ask for the length of this hypotenuse. Just depends. Make sure you answer the question. In this case, it just asks to solve for x. Number 6. So here, this is our last example. We again we have these two right angles here, and we want to find this length x. Since this was 9 and this was 12, we know that x and 25 are not parallel. So we want to make them parallel so that we know that opposite sides are congruent, and so that we can find out, using right triangles, what the length of x is. So we draw a line in here, and we get that that's 25 because that's the way we drew it, and then this would be 9, and over here would be 9. And then we know that the whole length of the radius is 12, so if we subtract 9, we get 3. So then this is a leg of our right triangle, because this is a rectangle, so all the angles are right. So then this one would be right by supplementary angles. So we get 3 squared and then 25 squared. This is right down here. And it equals our hypotenuse, which is x squared. We get 9 plus 625, and we get 634 plus x. So that equals x squared. We take the square root of both sides, and when we try to factor this down and simplify the radical, it doesn't work. So we can just plug this into our calculator and we get a decimal of 25.2. So our answer is x is approximately 25.2. Thanks for watching these notes. I hope they help. Any feedback you have, again, is very welcome, and I hope that they helped. Thanks.